So in our previous sections and studies of calc, we have talked about rates of change. A rate of change is an application of a derivative. So rates of change are super important in the real world because they can apply to everyday problems. So doctors use applications of rates of change when affecting dosages and how a body responds to them. Economists will use rates of change when they talk about how much it costs to produce steel at various levels. So the application that goes along with rates of change is one that can be applied to many everyday life activities. So the difference quotient is a variation of the slope of the secant line. It represents the average rate of change. So if you recall, the difference quotient again is our average rate of change. Right? The derivative, as we've discussed, is the limit as h approaches 0 of f of a plus h minus f of a all over h. So basically what happens in chapter 2 is we start with the definition of the derivative, and then we end with the definition of the derivative, but we'll use the power and product and quotient rules to understand it. So I'm kind of like just referencing it again because there are times like on a free response, it might say find the definition of the derivative and then do an interpretation of it. So I hate that I'm looking at it and doing it again with you, but know that it's more because we're trying to tie in how they relate. So, enlarging a circle. If you think about a circle, right, it can be expanded or contracted. And if you're changing the circle to expand or contract the area, what other part of the circle is changing? The diameter, the circumference. So they're changing, and would you say that they have to change together or separately? Together. A rate of change in calc shows us how they change together. So area of a circle is what? What's the area of a circle formula? Pi r squared. Okay, so area of a circle is pi r squared. I forgot to join my Zoom. So you're ready to see something very cool because I already hear you kind of like saying things. So we said area of a circle is pi r squared. If I ask you to find the derivative of area, that's like finding its rate of change. So that would be the derivative of area. It is with respect to the radius, and it becomes 2 pi r, which is exactly what you said, the circumference. It's the length of the period of a unit circle, yes. You get 0. No. All right, so if we evaluate the derivative of area, So A prime of 5 and A prime of 10, you get 2, 5, 5.
Following students, please report to the library at this time. Elijah Chip, Alicia Colson, Avery Mollick, Molly Sheets, Alex White, Emily Johnston, Dante Shuley, and Jada Spencer, please come to the library at this time.
So the derivative is a rate of change. So what does this represent? It represents the rate of change of the area as the radius is increasing. Here are you saying smart? Is he a freshman? Okay, because I don't have him yet. Oh, yeah, I mean in like advanced algebra 2. Because half those kids were my advanced kids from algebra 2 and the other half are freshmen. Oh, yep, sorry. All right, so then the last part of this extension is what are the units? What would the units be if the area is measured in square inches? So how do you find the units for dA, dr? Well, think about exactly, it's square inches or inches squared over inches, which is inches. Very good. So dA, dr has a unit of inches. And if you think about the circumference of a circle, what would its units have been? Inches. So technically those rates of change are also representative of the circumference at that instant. So the rate of change of the area of the circle, like we talked about, is directly related to the circumference changing with respect to the radius. See, you guys are so smart. So those of you that are in physics, this should be semi-easy for you because we're talking about motion along a line. Motion along a line is position. So the line or the position is that s-axis. And what we say is that an object is moving along this axis and its position is with respect to a function of time. So oftentimes you'll see position represented as s of t. Displacement is different than distance. So displacement is the total movement of the object over the time interval, where position is where that object is at that precise moment. So if I start here at this red block, that's my initial position. I could go 2 steps forward, and now my distance is, s of 2. I'm 2 steps forward. But if I would take 1 step backwards, my position is now back at 1, because I'm 1 position before where I started, but my displacement is 3, because I've taken 3 total steps. So your distance and your displacement are not the same. My distance is 1 unit from my initial position, but my displacement is 3. Does that make sense? My distance would be 0. My displacement is 4, because it would have been 2 steps in the positive direction and 2 steps in the negative direction. Good. I feel like that's always the tricky stuff. Yes. Well, we'll say forward and backwards, not necessarily the positive. So delta S is equal to your total change of movements over the total time. It's equal to your total change of movements over your total time. Average velocity is equal then to the average change of position divided by time, or your displacement over time. So displacement is f of t plus delta t minus f of t over delta t. And man, what does that look like? Yep, slope of the secant, or the definition of the derivative without our limit. So what do you think instantaneous velocity is going to look like? Yeah. So v of t is equal, because remember, this is average velocity, not the actual velocity, is the derivative of displacement with respect to the derivative of time, or the limit as delta t approaches 0 of f of t plus delta t minus f of t all over delta t. Now, speed is kind of like the difference between distance and displacement. Speed is the absolute value of velocity. Speed is non-negative. So it's the absolute value of velocity or the absolute value of the derivative. It is non-negative. So if you had a graph of velocity, the speed would be the velocity graph all in the positive quadrant. Acceleration. Acceleration is the second derivative of position. Acceleration is the derivative of velocity. So we say acceleration is represented by a of t, or the derivative of velocity with respect to time. Acceleration could be v prime of t. It can be equal to s double prime of t, or d squared s over dt squared. So again, this is more about notation than anything else. Those are all equivalent representations. So the best way to do this is through practice. So the last thing we want to talk about is the units or the constants for free fall. So where's my physics kiddos? Yeah. Not second though. What? Yeah. So if you're object is free falling, then it would, if it was falling to the earth, it would be negative. But yeah. But since we're just talking about the constants, that's talking about the acceleration essentially. So that's why the sign didn't matter. All right, so here is, this is actually something that your graphing calculator can do. And in physics, Mr. Mannion might actually have like the little readers, and it can, like, they're position readers. So like you can move forward and backwards, and it's like a camera, and it can record your motion. So this is a student in front of a motion detector. It records their velocity at 1 second intervals for a total of 36 seconds. It stores the data in the graphing calculator, and then we use that calculator to produce the following motion graph. So what we want to do is read this motion graph and discuss what that graph represents. So if this is the graph of position, when the graph is flatline, what does that mean the student is doing? Not moving. Perfect. So if the graph is flatline, the student is not moving. If the graph is going up, then our student is moving in what direction? The forward direction. So this graph, these units, since this goes 36, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 tick marks. So if it goes out 36 seconds, each tick mark represents how many seconds? 4. So it says describe their motion as a function of time. So if the graph is positive, the student is moving forward. So for the first 14 seconds, the student is moving forward. When the graph is negative, what's our student doing? So we would say from 14 to 26, they are moving backwards. And then here, where it's flatlined, what's my student doing? Go. And then 32 to 36, they're moving forward. So they're moving forward, but at like an extremely slow speed, almost to the point where the speed is 0. Okay. So then it says, when is her speed at a maximum? Yeah, kind of. So in terms of this graph, it is when she's walking backwards. It's going to be at this point right here, right? Because that is the steepest part of the graph essentially. So we would say her speed is at a maximum at about, it's like at that 22-ish, 21-ish second mark. It's hard to see. You could even maybe say 20. It's very open to interpretation. Okay. And then the rest of this, like the rest of today, I think you're going to like a lot because it's really going to just be derivatives and finding values at derivatives. So what would the velocity of this position graph be? So it's acceleration. And if S is in meters and T is in seconds, what would my velocity units be? Good? No? Okay, yeah, acceleration would be meters per second squared. And again, it all has to do with taking that derivative with respect to time. Correct. Yep. We did. So if you think about velocity, it's the derivative of position with respect to time. It's ds dt. So I'm not making you do the definition of the derivative anymore. There, yeah, we know that, like, yes. Nope. We're beyond that. That's what I said. Like today is like the happy day. It like goes back to what we did in chapter 1. Yes. What? For this? Probably like late next week. Everything. Yeah, but this is the last lesson of chapter 2. Here's the thing though, really, like, okay, I gotta pause this. Comfortably, I know, get through your homework. Find the acceleration after 1 second. Instead of doing the limit with a equaling 1 plus h, you can now just find a of 1. And this is why the physics kids hated me for the past few weeks, because they learned this a while ago. Okay, find the acceleration at the instance when velocity is 0. So you have to set the velocity equal to 0. Exactly. So you find when velocity is equal to 0, which is 2 and negative 1. However, can time be negative? So you can actually even throw out the negative time. And then a of 2 is equal to 12 times 2 minus 6, or 24 minus 6, which is 18 meters per second. So velocity being equal to 0 is like a horizontal tangent. Does anybody remember what a horizontal tangent represents on the original graph? An extrema, exactly. It represents a max or a min. So what that means is that when the velocity is equal to 0, the position or the function is changing direction. Yep. So the only thing that goes along with this is with displacement. So we started with displacement, right? So the displacement comes with when the function changes position. So when does the function change position? When the velocity is equal to 0, exactly. So in order to be able to do this, you have to find your velocity, find the zeros of velocity, so what that means is that it changes direction at time 2. So your displacement over those first, whatever seconds would be s of 2 minus s of 0. Because it's final minus initial. Sorry. We'll pick up with this on Monday.